A very warm welcome, my dear students. I'm Aarzoo and I'm here to simplify physics for you. If you are preparing for CBSE 12 Physics exams 2027 and you want to understand physics in the easiest possible place, then you are in the right place. Every Thursday, I upload one complete CBSE physics topic with PYQs. So today I'm here with electric potential difference and electric potential. So let's get started. So over here I have electric potential difference. So let us try and understand what is electric potential and what is electric potential difference today. So to start with, the electrostatic potential difference between 2 points in any electric field may be defined as the amount of work that we do per unit positive test charge in moving it from one point to another against the electrostatic force due to the electric field. So let us try and understand what this means, okay? So firstly, over here I have a charge at O, which is plus Q charge, okay? This plus Q charge is producing an electric field all around it. And due to this, there's electric field around everywhere, and there are these points A and B, which are a part or which are the points in this electric field. Now I have a test charge Q0, which I am trying to move from A to B, and of course I will have to do some work against the field that is coming due to plus Q. So now if I want to write the electric potential difference between the points A and B, then I can write VBA as VB minus VA. That's the potential difference between the points A and B. And this, as per definition, is simply the work done in moving the charge from A to B against the electrostatic field divided by the test charge, because we want to find it for a unit positive charge. Now, further, I know that in order to find out the work done, I should be able to write down the force first. So let's say that the work in moving a small part dl over here is simply F dot dl, and I'll have to integrate it from A to B. So I can assume that the distance of A from O is RA and the distance of B from O is RB. So I have to integrate it from RA to RB. Now, in order to write down the force, we already know that the force that this test charge would experience would be equal to negative Q naught by E. Why negative? Because I'll have to do work against the electric field or the electric force, because both of these are positive charges, so there will be repulsion between them. Now, over here, I can substitute this value of force, that is minus Q naught E. So my dW would simply be equal to negative Q naught E dl, and I have to still integrate this expression from RA to RB. Now, further, I also know that the electric field at point P, let's write it, it would simply be equal to KQ by R, or KQ by R I can write, then I'll have to, instead of taking dl, over here distance is dr, so we will change it into dr. So over here, let us substitute the values. So I'm trying to integrate from RA to RB, and Q naught remains Q naught. Instead of E, I am substituting KQ by R square, and because I'm taking the distance in terms of R, therefore instead of dl, I'll replace it with dr over here. Now, let us try and integrate. The integration of dW would simply be WA, and this is the work done in moving the charge from point A to point B. Further, over here you can see that K, Q naught and Q, they all are constants. So let us take them out of our integration, and we are left with 1 by R square dr, and again my limits are there, RA to RB. Further, I can write down over here that this work done will simply be equal to 1 by R square integration would be 1 by R. So I have 1 by R, and I need to substitute the limits, that is RB and RA. So from here, I simply get my work done as minus KQ naught, QQ naught upon 1 minus RB minus 1 by RA. Now if I take the negative sign inside, the work done would simply come out to be K Q naught Q times 1 by RA minus 1 by RB. This is the expression for work done in taking the charge from point A to point B. That's a very straightforward one, so we have just integrated the expression. Now further over here, since I defined VB minus VA as the work done in taking the charge from A to B by Q naught, so now let us simply try and use equation 1 and substitute the work done expression there. So work done is Q naught into 1 by RA minus 1 by RB, and I'm supposed to divide this by Q naught as per equation 1. So Q naught gets cancelled, and my potential difference between the points A and B simply comes out to be KQ times 1 by RA minus 1 by RB, where Q is the charge who's producing the electric field and RA is the distance of the point A from O, and RB is the distance of point B from O. So this is electric potential difference. Now, with a small variation in this electric potential difference, we can actually define electric potential. Now, electric potential at a point, the only difference between the electric potential difference and electric potential is that when we are defining electric potential difference, we talk about taking the charge from point A to B. So we are talking about two different points, that are A and B. Over here, if one of the points is taken as infinity, then that means you are defining electric potential. So there we had written the potential difference between A and B. So here basically the potential difference is between A and infinity. So instead of point B, I am taking infinity. So this is the work done in taking the charge from infinity to a point. Okay, now by default we assume that the potential at infinity is 0. See, the potential, the 0 of the potential is arbitrary, so you can assume it to be 0 anywhere, but by default we assume it to be 0 at infinity. So since my V infinity is 0, therefore my expression reduces to VA equals to the work done in taking the charge from infinity to point A. Now actually if you look in carefully and come back here to the electric potential difference, we have already integrated and everything is there. So I will directly use this expression of work AB, okay, and I will write it here. The only difference would be that this time, okay, sorry, I forgot to divide it by the charge Q naught here. The only difference here would be that when I write the work done from taking the charge from infinity to A, my limits would be different. Over here my limits were RA and RB. Here my limits would be infinity and RA. So this is simply equal to minus KQ Q naught, and I'm integrating it from infinity to RA. That's the only difference. Okay, the integration will still come out to be 1 by R. So your work done in taking from infinity to point A would be negative KQ Q naught into 1 by R, and I have to substitute RA and infinity in this. So over here the work done in taking from infinity to point A is negative KQ Q naught into 1 by RA minus 1 by infinity. Okay, now the work done, we already know that 1 by infinity is going to be 0. So the work done from here simply comes out to be KQ naught Q by RA. This is the work done in taking the charge from infinity to a point A. Now as per definition, again if I use equation 1, then VA minus V infinity, or simply VA, can be defined as KQ Q naught divided by Q naught times RA. So Q naught gets cancelled, and my potential at any point A can be written as KQ by RA, the distance of A from the charge Q. This is the expression for electric potential at any point. So the difference is only between infinity and a point, and between 2 points A and B. Now electric potential is a scalar quantity. So here the direction does not really matter. Also, we would measure any type of electric potential or any type of potential in volts. So the unit for potential is always volts. It's a scalar quantity. So I hope everything is clear till here. In case you have any doubts, then don't forget to write it in the comment section and I'll be happy to address them. Also, take a few seconds and do subscribe to my channel. Further, moving on to the electric potential due to a system of charges here. So I have charge Q1, Q2, Q3, Q4. Let's say we have Q2 here, Q3, Q4, and you have so many charges till Qn. Okay. Now I want to write down the electric potential at this point P. So the electric potential at this point P would be the sum of the individual electric potentials. Now, since electric potential is a scalar quantity, therefore when you substitute here, whatever is the sign of the charge, you just substitute with that particular sign of charge. So if I want to write the electric potential at this point P, I can write the potential V1 as K Q1 by R1 plus K Q2 by R2, so on till K Qn by Rn. This is the sum of electric potentials at this point. If I want to write a general expression over here, then my general expression can be written as the electric potential at any point would be equal to K times the summation of all the charges from 1 to n going from Qi to Ri. So this is the expression for electric potential due to a system of charges. So again, it's a scalar quantity, so we are directly adding, no vector addition. You don't need to worry about any of the directions, only the signs. If Q1 is positive, then substitute Q1 is positive. If Q2 is negative, then substitute Q2 as negative. Whatever are the signs of the charges, substitute as per that only. So now we have understood electric potential difference, electric potential at a point, and also electric potential due to a system of charges. Now next, we should move on to writing an expression for the electric potential at any point due to an electric dipole. So dipole means I have a negative Q charge and a plus Q charge which are separated by the distance 2a. So over I have the dipole at points A and B which is separated by a distance 2a. O here is the center of the dipole. Now I want to write down the electric potential at this point P, which is from the center of the dipole, you can see its distance is r, and from the charge at A, the distance is PA, and from the charge at B, the distance is PB. So let us try and write down the electric potential V1. Now this one is due to the charge at point A. So this is due to minus Q. Okay, so I can directly use the electric potential expression, that is minus KQ by PA. So you can notice here that I have taken the charge to be negative and that's why I have written a negative sign there. Similarly, I can write my V2 which is simply going to be KQ by PB. So this is the electric potential due to plus Q. Now I have the electric potential due to plus Q and due to minus Q. Now we already know that the electric potential at this point P would be the sum of the individual electric potentials. So let's directly add it. So I have KQ by PB minus KQ by PA. To calculate the value of PA and PB, let us look in here. So firstly, we have drawn a perpendicular BN to OP and AM to MP as well. Now further, if you look in triangle AMO, so we are looking in triangle AMO. Now in this small triangle AMO, you can see that OM will be equal to A cos theta. Further, now if this dipole is small, so in case the length of the dipole is small in comparison to the distance r, then we can say that PA is approximately equal to PM. And further, PM can be written as PO plus OM. And therefore, the value becomes, so I can say that PA is equal to PM and PO plus OM would be equal to, so PO from here you can see is R and OM as I wrote in here is A cos theta. So the value for PA would be R plus A cos theta. By using a similar logic, I can similarly say that the value of PB will be equal to R minus A cos theta. So now I've got the value for PA and PB. Therefore, let's move on further and let's start substituting it. So my VP, which I have written as KQ by PB minus KQ by PA, let's take KQ common outside and I'll have, instead of PA, I'll write R plus A cos theta, and instead of PB, I'll write 1 upon R A cos theta. So 1 by R minus A cos theta minus 1 upon R plus A cos theta. So now after substituting these values, we are simply supposed to simplify. So VP can be written as KQ into. So this is R plus A cos theta minus A plus A cos theta upon. This is A square minus B square, so R square minus A square cos square theta. So over here VP is equal to, this is KQ into. So this is 2A cos theta upon R square minus A square cos square theta. Okay, now 2AQ is nothing but the dipole moment P. Therefore, VP can be written as KP cos theta upon R square minus A square cos square theta. So this one is my final expression for the potential at a point P due to a dipole. Now over here you can also do some specific cases. So for example, if you want to talk about a specific case, for example, let's just talk about a simple, very easy one. If I'm talking about an axial line, now for the axial line, we know that theta would be equal to 0 degrees. If theta is 0 degrees, cos 0 is 1. So if I put cos 0 over here, then I will simply get my VP as KP upon R square minus A square. And whereas on the second situation, if I talk about the equatorial line, on the equatorial line, my theta would simply be equal to 90 degrees. Now since theta is 90 degrees and cos 90 is 0, therefore then my VP would be equal to 0. So this is all about the electric potential at any point due to an electric dipole. Let's move further ahead and talk about the electric field as a gradient of potential. See, electric field can also be calculated by simply differentiating the potential with respect to distance or length. That is why we say that electric field is a gradient of potential. Now, there is a negative sign here, and this negative sign that we are talking about, it is telling us one very basic thing. It is telling us that the direction of your electric field will always be in the direction of decreasing electric potential. So, we will simply say that the negative sign here indicates that the direction of electric field will always be in the direction of decreasing electric potential. You should learn this equation because this equation is important from your board point of view. for your CBSE board papers, the MCQ questions are very commonly asked on it. They'll give you an expression for potential in terms of the distance, that is R, and they will ask you to find electric field. To find the electric field, you just have to differentiate it. Okay, that's all that you need to know about the electric field as a gradient of potential. Even in NEET, such questions are important. Okay, now moving further ahead, we are going to talk about the equipotential surfaces. So what exactly are these equipotential surfaces? Let's break the name. See, equi means of course equal, and potential means electric potential. So these are those surfaces which have the same potential throughout. So we can say that any surface which has the same electric potential, any surface which has the same electric potential throughout, or you can say same electric potential at all the points on the surface, is called an equipotential surface. Very basic, simply go as per the name. Now if you look at the name, it's very easy to understand it, but then these equipotential surfaces, they have certain basic properties, and we are going to study about their properties, or we are going to learn about their properties one by one. So firstly, if you talk about the first one, so there is no work done in moving a charge over an equipotential surface. No work is done in moving a charge through an equipotential surface. Why? Now the question is that why there is no work done when we are moving any charge through an equipotential surface. Now if you remember the definition of the potential, then you would be remembering this very basic equation. I told you that VB minus VA is equal to work done by the charge. Now since VB minus VA is 0, since it's an equipotential surface, so there's no potential difference, therefore the work done in going from A to B will also be 0. Now the second property. The second property simply tells us that your electric field will always be perpendicular. Will always be perpendicular to an equipotential surface. You can see on the diagram also that my electric field is perpendicular to the equipotential surface because there is no work being done. If there's no work being done, that means the dot product of E and S has to be 0. So that is only 0 when your angle over here is 90 degrees. So this is an equipotential surface. You can see that the electric field is perpendicular to the surface. Thirdly, now if you have an equipotential surface, just by looking at the different equipotential surfaces, we can figure out which side is the field stronger, which side is the field weaker. So if you have an equipotential surface, see the equipotential surfaces, we can say that they would be closer in a stronger field and they are weaker when they are far away. And you can say and the field is weak when the surfaces are far away. Or you can say when the surfaces are farther. That's one and the same thing. So the closer the equipotential surfaces, the stronger will be the electric field in there. And lastly, two equipotential surfaces can never intersect each other. Two equipotential surfaces can never intersect each other because if they will intersect, then there would be two different values of potential at that very point, and that is not possible. So these are four main properties for equipotential surfaces. I will quickly repeat them. No work is done in moving a charge to an equipotential surface. Electric field will always be perpendicular to an equipotential surface. Equipotential surfaces can tell you how strong is the field. The closer the equipotential surfaces, stronger is the field. And lastly, two equipotential surfaces can never intersect each other. Now, let us look at some equipotential surfaces here. The first diagram that you see over here, this one is showing you multiple equipotential surfaces for a positive charge. So you can see that if you have a positive charge, the electric field lines are outwards. These arrows are showing you the electric field lines, and these circles that you see, they are your equipotential surfaces. Now you can see that the distance between the equipotential surfaces is increasing as you're moving outwards. That is simply because the electric field reduces, or the strength of the electric field decreases as we move away from the center. This one, the one on the right, is showing you equipotential surfaces for a uniform electric field. Since it is uniform electric field, therefore my equipotential surfaces are equidistant. The distance between each of these planes is same. At the bottom over here, we see that there are two positive charges. Again, you can see the field and you can see the equipotential surfaces. So this is when you have two same charges, like positive or negative. And the last one over here in the corner is an electric dipole. For an electric dipole, you can see that because both the charges are same in magnitude, therefore you just have equipotential surfaces in the form of these circles, concentric circles. Again, for these circles also, you can see as you're moving outwards, the distance between these concentric circles is increasing, and that is simply because as we move away from the dipole, or as we move away from a charge, the electric field strength reduces. Now, since we have understood everything about the electric potential, equipotential surfaces, and how to deal with these, let's start working on some questions. So let's look at the first question in here. At a point, due to a point charge, the values of electric field intensity and potential are 32 Newton per coulomb and 16 Joule per coulomb respectively. Calculate the magnitude of charge and distance of the charge from the point of observation. So let's make two equations. First one is electric field, which is simply kq by r square, and this will be equal to 32 as given to us in the question. Let's label this as equation 1. Then second one is for electric potential. My electric potential would be kq by r, and this is given to me as 16 from the question. This is equation 2. Now they want us to find the charge and the distance, so we just have to simplify these two equations. So to start with, we can simply divide equation 1 with equation 2. So I would have kq by r square times r by kq. This equals to 32 by 16. So I can cancel whatever I can, and from here my r comes out to be 16 by 32, which is simply 0.5 meters. So I've got the distance here. In order to find out my charge, I can simply find out, like I can substitute in any one of these equations, either the electric field or the potential. So I'll substitute in potential since it's easier. So 16 is equal to k, which is 9 into 10 to the power 9. Charge I want to find out, and my r I got as 0.5. So over here, you can simply see that I'll have 16 times 0.5 by 9 into 10 to the power 9 equals to q. On simplifying this, my charge simply comes out to be 8.89 into 10 to the power minus 10 coulombs. This is the value of charge. It was an easy question, straightforward one, just direct formula application. Now, let's move on to the next question here. So calculate the potential at the center of a square that is ABCD of side root 2 meters due to the charges 2, minus 3 and 6 microcoulombs at the four corners of it. So let's quickly make a square in here. So let's say this is my square. So I have A, B, C and D. At point A, I put in the charge 2 microcoulombs. At B, I have minus 2 microcoulombs. At C, I have minus 3 microcoulombs. And at D, I have minus 6 microcoulombs. I want to find out the potential here at the center, and the center point, let's just call it O. Now the side is given to me as root 2 meters. Now further over here, if you look in carefully, we can simply say that this distance, or this distance, or whether it is this distance, all these distances are equal. So I can say that OA is equal to OB is equal to OC is equal to OD, since it is a square. Also, these are 90 degrees because we know that the diagonals of a square bisect each other at right angles. So if this distance is R, this distance would also be R. Now if I look in triangle AOB, I can use Pythagoras theorem here. AB square will be equal to AO square plus OB square. AB square is given to me as root 2, so root 2 whole square, and this is R square plus R square. So this is 2 is equal to 2R square, or in other terms I can say R is equal to 1 meter. So my distance comes out to be 1 meter. Now, if I want to write the potential at the point O, then that would be equal to the potential due to the charge at A plus the potential due to the charge at B plus the potential due to the charge at C plus the potential due to the charge at D. Why am I adding all these? Because we already understand that potential is a scalar quantity, so I can directly add them. So VO can be written as, this is KQA by R plus KQB by R plus KQC by R plus KQD by R. Now I can simply take the KQ common over here and I'll be left with, sorry, not KQ, I can take K by R common. So in order to take K by R common, I am left with QA plus QB plus QC plus QD. Now let's just substitute the values. V0 would be equal to 9 into 10 to the power 9. R we have calculated as 1 and the charges. Now I have 2 into 10 to the power minus 6 minus 2 into 10 to the power minus 6 minus 3 into 10 to the power minus 6 minus 6 into 10 to the power minus 6. Sorry, this is plus 6. Now if I add these and I multiply with 9 into 10 to the power 9, my V0 comes out to be 2.7 into 10 to the power 4 volts. This is the value of potential at the center of the dipole. So this is all about this question. I hope you understood it. If you understood electric potential today and you enjoyed solving all these questions, then do subscribe to my channel and I hope to see you next Thursday again.